Okay, so we will be doing a derivation of Kepler's third law in this video. And so Kepler's third law basically says that the square of the period of a planet's orbit is proportional to the cube of the orbit's semi-major axis. So that's just stating that the period squared is proportional to the semi-major axis cubed, where A is the semi-major axis. And just a quick diagram of an ellipse. That's the major axis, that's the minor axis, and then if you just cut it down in the middle in half, the semi-major axis is half of the major axis. So in order to do this derivation, we must take into account a couple things before we start. We can imagine that a planet is in orbit around, let's say, the sun or a star or something like that. That's a focus of an ellipse. And so we must assume that there are no net external forces, and the only force acting is gravity on the planet. And so you just have gravity, and since gravity is a radial force, it's going to be pointing centripetal. So you can assume that the net forces MAC, and then you can say that the force of gravity is equal to MAC, your centripetal acceleration force. And we know from the past that the force of gravity is gmm over r squared, and acceleration centripetal is equal to v squared over r. So we can set this equal to mv squared over r, and right away we can see that one of the masses cancel out, and even one of the radiuses cancel out. So you're left with g m over r is equal to v squared. And then from past experience, we know from circular motion, you can say that the velocity of an object in circular motion is equal to 2 pi r over period. And so we have velocity here. We can just put it right in and have 2 pi r squared over your period squared, which gives you 4 pi squared r squared over period squared. And so now, to make it look like this equation that Kepler's third law, t squared is equal to ka cubed, we want to isolate t. So we can right away cancel one of the r's from both sides. Or no, not cancel. We're going to end up multiplying, so my bad. So you can come to here and say gm is equal to 4 pi squared r cubed and over t squared. And so with some simple algebra, you can bring the t squared over and bring that down, and you're left with 4 pi squared r cubed over gm. And so to make it look like Kepler's third law, we can write it right down here. You can see that we have a cubed right here, which is your semi-major axis, and in this case you have r radius, which is also equal to semi-major axis, so we can just set r equal to a. And then we must figure out, well, what's k? K is just a constant, so we can isolate out the constants in this right here, is in this equation, and we can see that 4 pi squared over gm is essentially a constant, because pi is a constant, g is a constant, and your mass is going to be known, so that's a constant as well. And the only thing you have left is r cubed, and r is equal to a, so essentially you're getting t squared is equal to k a cubed, where k is equal to 4 pi squared over gm, and a is equal to r. So once you look at it from a broader scale, in the equation, or Kepler's third law, it states the period squared is equal to a constant times your semi-major axis cubed. So you can, through this derivation, you can see that your k, or constant, actually, once you do the derivation, actually equals a value that we solved for here, that we found whenever we plugged through our equations, and we found that's equal to 4 pi squared over gm. And you have your r cubed equal to a cubed, and you're left with Kepler's third law. Thanks for watching.